opportunity to speak to you about some of our efforts to identify MOFs for carbon capture applications. So in particular, what I'll talk about today is our work on looking at solid sorbents for removing CO2 from post-combustion flues. So here it's a gas separation process where we're removing CO2 mostly from a mostly nitrogen-based gas stream that's also humid, and you want to pull out at least 95% pure CO2. And well, porous solids have been doing this, scrubbing CO2 from natural gas for many decades now. And they've been using these pressure swing absorption systems where these big beds here are actually full of zeolites. So problem with zeolites is they don't function with any humidity. And of course, combustion flues have water since it's a major product. So new sorbents are needed, and this is where the kind of materials we look at, metal organic frameworks or MOFs, have attracted a lot of attention. So these are materials built from organic and inorganic linkers that can self-assemble to form hopefully a porous network material. And you can combine different linkers to form different structures. And in fact, tens of thousands of MOFs have been experimentally characterized, or porous MOFs have been experimentally characterized with an astonishing array of pore chemistries and pore geometries. And so these materials have attracted a lot of attention for CO2 capture. In fact, we've been involved in the commercialization of the first MOF to be used for CO2 capture at the industrial scale. So this is the MOF CAP20 that was first developed in George Shimizu's lab at the University of Calgary and is being commercialized by Savante, also a Canadian company, to pull CO2 from cement making. And they've been doing this with this material for more than 3 years, and now they're scaling it up. So it's a great material, but the material works well for Savante's proprietary process. It doesn't work well for PSA. It doesn't work for humidities greater than 25%, so they're trying to fix that. And also, it doesn't work well for low CO2 concentration fluids. So cement making is greater than 20%. So there's still a need to find new materials, and of course, MOFs are still interesting, and the modular nature makes them amenable to applying data-driven methods, which is one of the themes of this symposium. So, and we've actually been involved in data-driven machine learning and high-throughput screening studies for some time. In fact, our early work was the first sort of machine learning studies of MOFs, and more recently we've gotten in the business of developing, I'll call them clean databases for screening and developing machine learning models. So when you're doing the screening, what most people are looking at for post-combustion CO2 capture, traditionally people look for two properties: high uptake and high selectivity. So experimentally, they measure this with these gas absorption isotherms. So this here is they're measuring the millimoles, say, of the CO2 that the material can capture per gram of that material as a function of the partial pressure. And so this material absorbs a lot of CO2 compared to N2. So it has both a good uptake and a good selectivity. And so in these high throughput screening and machine learning models, mostly what's done is the isotherms are not experimentally derived, but they're derived from simulation. And okay, So, these are done, this is supposed to be a movie, but I guess it's not working. We use grand canonical Monte Carlo simulations, and these basically a brute force method. You move these molecules, these CO2 molecules are supposed to be moving, and you calculate the interaction energies millions of times. And so we're using pretty simple force fields, but to get good results, we're usually using DFT-derived partial atomic charge parameters. And if you use the experimental structures, you can typically get reasonable agreement with experiment. So we generate data computationally, typically, and this allows you to do screening. And like I said, most screening studies look at just the capacity and the selectivity. And as an example, one of the sort of famous MOFs for CO2 capture is this magnesium MOF 74. It has the record CO2 capacity somewhere around 8 or something, so much higher than this one. It's a poster child, so sort of say for CO2 capture. But we started to ask ourselves, how well will these actually work in a real plant? So if you put these MOFs in a real PSA system, can they really lower the energy costs of CO2 capture? Can you actually achieve the 95% purity that you need for transport? What properties are actually important? Do you really need ultra high CO2 uptake, or does the performance sort of scale with the uptake, or do you just need sort of a certain threshold? So these are all good questions that you can't get from these simple equilibrium metrics that people screen for. So to look at these problems, you really need process simulations, and we started to collaborate with a brilliant process engineer, Arvind Rajendran, who's at the University of Alberta, and he's developed some sophisticated models of PSA systems. This is one sort of a common 4-stage PSA cycle, and the models are macroscopic, but they account for, they're very detailed. They account for the frictional pressure drop. So if you pack it with smaller beads or whatever, the pressure drops are higher, then the energy costs are higher. Accounts for temperature, concentration changes due to absorption, of course, heat transfer, because when you absorb, you're giving off heat, and then, known pump and vacuum efficiencies. And importantly, these models, at least for PSA, have been validated at the pilot scale with real materials. So with these models, some of our first collaboration involved integrating the atomistic simulations with the process models. So we do these atomistic simulations, and we derive the gas absorption properties, heats of absorption, for example, even heat capacities, and you can also get some diffusion coefficients if you wish. So these then are fed into these detailed process models, and for every MOF, the process conditions are optimized. So, for example, how strong of a vacuum do you apply? How long do you apply the vacuum? How fast do you feed the gas? So these are all optimized in order to or minimize the energetic cost of CO2 capture, with the constraint that you're getting out 95% pure CO2. So this is done for every MOF, and that's actually a quite time-consuming simulation. So our first work, we actually screened about 1,600 experimental MOFs. So these are known MOFs, and we did it for combustion flues related to cold combustion, so that's about 15% CO2. And here I plotted the results, only showing the top 150, so they're sort of all cut off here, but this is the energy of the CO2 capture and the selectivity of the absorption properties that we get. Now, interestingly, magnesium MOF 74, which I said is this record holder, has by far the largest CO2 capacity, isn't even in the top 150, which is interesting. And we also note that there's actually a wide range of selectivities. You can get rather low capture energies with a range of selectivities. So it seems there's multiple ways if you to optimize the process conditions to get low capture, even if you don't have the highest selectivities. So the lowest MOF, which is sort of by itself here, is very interesting. So ICER MOF, it has an unusually low N2 uptake. And it turns out that low N2 uptake is important for low energy. In many ways, so once you get to a certain selectivity and uptake capacity, the N2 uptake becomes important. And so that was one of the biggest conclusions of this work. And in many ways, people have been looking at targeting the wrong properties, at least for PSA-based CO2 capture. So another interesting thing is it's sort of, there's a cluster of MOFs that have, this sort of energy, but ICER MOF, which is significantly lower, is sort of by itself. And so it'd be nice to see, is this a one-off thing? Is this really unique? How unique is it? I mean, we would love to screen more experimental MOFs, but this study itself already took more than 860 years to complete. So what we've done more recently in a new collaboration is to start looking at machine learning to accelerate the screening process. So where are the bottlenecks? Well, at least in the atomistic simulations, it's not actually so much in the GCMC simulations to get the absorption isotherms. It's in many ways to get DFT-derived charges to perform those simulations. And so for the largest MOFs, that can take hours to days per MOF. So that's one thing we wanted to attack. And the process simulations, they themselves, a single process simulation doesn't take long, but you have to optimize all those parameters for every MOF. And that can take, usually takes days per MOF. And that's why those simulations or that study took so long. So we need to attack these bottlenecks. And the first one we did was to get these partial atomic charges. So just to say what they are, basically, we're using a pretty simple model where we have fixed partial atomic charges assigned to the atoms, and that's how we calculate the interaction energies. And unfortunately, these charges, if you change a functional group, there's a large redistribution, and so you sort of have to recalculate the charges for every MOF that you screen, and so a single point DFT calculation, like I said, for some of the larger MOFs can take hours to days to complete, at least with the computing resources that we have. So, of course, machine learning is a great way to get these charges. And when we started the project, there were 3 machine learning models to get these partial atomic charges trained on specifically MOFs. So, and they gave very good mean absolute errors. So in units of electrons. 0.02 is actually really good compared to the DFT calculation. But they were trained on, well, the whole training and test sets were less than 3,000 experimental MOFs from the so-called core database. And last year, I presented a talk where we were looking at errors in this core database. So it turns out this database has a large fraction of chemically invalid structure. So this is the structure and core of this MOF, say, do, and the yttrium has a +7 oxidation state, which is impossible. So it turns out the real structure, these oxoligands are actually aqua ligands. And so they have the wrong structure in this core database. And in fact, about 50% of the structures in this highly used and cited database of experimental MOFs is actually has these types of errors. And so we're finally able to, well, allowed to publish this work that I presented last year, and it's in press now. So we developed our own machine learning model, and we trained it. This is just the training set is about 250,000 MOFs that we have DFT calculations for. And those MOFs were cleaned up so they don't have the same sort of errors that the core database have. And so we ended up with about 40 million charges to do the training on. So these are partial atomic charges. And I won't get into it too much, but we used a graph attention neural network, which is a bit more advanced than the previous models. And we were also able to get an MAE at about the same level on a test set of 28,000 MOFs. Okay, so, and the overall calculation time to get the charges for every atom in the MOF on average on this test set was less than 2 seconds. So it was a big improvement in terms of time to get the charges. And the charges are good, and I like to show this violin plot, but what this is on the left is the DFT-derived charges. So that's our ground truth. And for all the atoms in this test set, it's the distribution, say, for hydrogen. So all of the hydrogens in this test set, the distribution is roughly centered around 0. And with our machine learning model, it's basically a mirror image, and it's the same for all different elements. So this is gives you an idea that this machine learning model is fairly accurate. And if you actually calculate an observable with this property, so if you calculate them with those ML charges versus DFT-derived charges, the correlation is very good. So this is the CO2 uptake calculated with the ML and with the ground truth charges. Now, this is a big improvement over the QAQ charge models that are in wide use before machine learning came into play. And you can see there the green is not as good. So this is a big improvement in speed and accuracy. So I think we've at least helped with this part. Now for the detailed process models, which can take days or longer to complete, well, Arvin's group developed a clever Canadian name, this Maple model, but it's pretty simple. It's just a normal, neural network with inputs, the inputs being all these parameters and the process conditions, and then it spits out the energy cost and purity of the CO2 with those specifics as input. And so this model then allows us to do the process simulations again, to do a full optimization for a moth, about a minute versus days. So now with this sort of accelerated process level screening, we were able to screen about 23,000 moths, and this is now with our own database that doesn't have those errors in it. And so we were previously only able to screen about 1,600 moths, and whoa, okay, so we screened. You can't see them, but 3 different concentrations: 6%, which corresponds to natural gas combustion, 15%, which is coal combustion, 35% CO2, which corresponds to steel production. And so we screened those 3 flue gases, and we screened with water where no other screens have screened with water before. So these are the results, at least with the coal combustion, of 15% CO2. And here I'm showing the Henry's constant of CO2 absorption and N2 absorption. Again, you can see how important the N2 is, uptake is. But basically, the colors here also, the more blue it is, the better. It's lower energy. And the gray moths are actually moths that no matter what conditions we use, we could not get this 95% purity. And so the dark blue moths, which are sort of in this region, are the lowest that we could identify. And you can see this ice-surf moth is in there. If you remember, in our previous screening, ice-surf moth was sort of by itself. But here now we can find about 2,300 moths within 10% of the lowest, and it's also a bit lower than ice-surf moth. So we can actually find lots of potential candidates, which is good because the moths have to satisfy lots of other properties that we can't always simulate. So what we then did was, these were the moths that were within 10% of the lowest energy under dry conditions. And then we did simulations, 3-component simulations with CO2, N2, and water at 40% relative humidity. And when we screened those, we were left with, from thousands to hundreds, that still retain their CO2 uptake capacity. And so, interestingly, and a lot of the moths in these 3 concentrations are the same, but of the unique moths, about 40% of them share this structural feature. They have straight, narrow 1D channels, which appears to be good for capture under these conditions, under humid conditions. So what about the validation of the screening? Well, so we came up with sort of a top 10 list for synthesis by very carefully looking through our sort of high performers and going through the literature, looking for any red flags, looking for water stability and those things. And we came up with a top 10 list, and our synthesis partner started making them last summer. And so far, they've attempted to make 2 of the moths. The first moth, they could not reproduce the synthesis that we reported. But the second moth, I would say, has been a hit. And they've now since been able to synthesize a whole family of these moths with one functional group that's modified. And a few of them have been experimentally determined to capture CO2 at high relative humidities, really high relative humidities. And they also now try to synthesize, well, they have a new derivative that's never been reported, that's extremely stable water, acid, and base as well, and they can easily synthesize it at the gram scale. So now our Arvin's group is looking at this model to see how it really performs in a PSA system. But interestingly, oddly, this family hasn't really been studied for CO2 capture. So it's been looked at for other properties, but so there's some opportunities that we think we've been able to identify for this family of MOFs. And like I said, this a few of them are particularly stable. So that's sort of what I wanted to present, is to show you our screening of CO2 capture materials for this specific process. And so we've sort of integrated our atomistic and process modeling for CO2 capture. And that's sort of important because you know, we can be looking at the wrong properties if we don't consider the actual process. And I think I've shown you that we've used machine learning surrogate models to screen our materials faster, and we've actually identified and experimentally synthesized and confirmed that at least a few of these materials that we've identified perform well. And then I guess I'd like to thank the members of my current group, the ones in blue contributed to this work I presented, and then our collaborators, most notably that funds a lot of this work, Total Energies, and I'd like to thank you for your attention.
The bottleneck you identify of DFT-based challenges, right? For the kind of system you're talking about, something much more, much more CPU non-expensive like DFTB would probably do the job almost as well as DFT.
Yeah, it's possible. We haven't evaluated that, but now we have a model that does it.
Okay, so it is a slightly conceptual question.
I mean, I should say our pipe binding calculations on loss, we did try to do some geometry optimizations, and it did not perform very well. At least on MOFs. So maybe the charges might be okay, but at least our experience with at least with the broad array that we have of MOFs, it doesn't perform well, at least for certain properties.
And so maybe more like a comment that there's this one track to use semi-empiricals, right, to accelerate things. And another one is, okay, ground truth is BFT and the machine learning model on top of that. And just this comparison is already very interesting, right? Like, is it that I'm better off incurring the cost of BFT and the machine learning on top of it? Am I better off in terms of accuracy versus a track where I'm just outsourcing everything to DFTB? And I'm not sure which pipe binding calculation you use. There are multiple flavors. The XTB ways, there is a DFTB way with pairwise parameterization, XTB way, there is a second-wise parameterization. There's still some lack of literature on comparing these different options to go into wider scale. It would be very interesting.
Yeah. Well, a few years ago, we did look at different pipe binding models, and yeah, they all have this problem with geometry optimization. So, but you might be right with the charge properties, it might be okay. But like I said, for geometry optimization, it was, yeah, to say the least, pretty bad.
Which pipe binding was it?
Well, like I said, we used ones with the atom pairwise ones, and we've tried, DFM
And you didn't.
Yeah, and none of them were. Yeah.
Next question. Very quickly.
So I'm curious about the errors you mentioned in the system, in the defense, for here, I think it was the name. Where are these errors coming from? Or what's the reason?
Oh.
A few words about that.
Yeah, so, the errors, that's a good question. So just show you an example here. So all of these structures are derived from the CSV, which are single crystal X-ray structures. And that experimental technique doesn't resolve protons very well. So all the protons you see are typically added with an algorithm, but the algorithm doesn't work well when we're close to a metal. And so when people deposit it, this was the way it was deposited without the protons. You go to the original paper, it talks about these being off-the-ribbon. But they don't know where the positions are, and they don't, they know it's an off-the-ligand, so they don't put it in. But when they took these structures, they didn't realize this sort of problem. So that's one thing. The other thing is these MOFs are usually activated with, so they're crystallized, with solvent in them. And so they have a solvent removal algorithm. And it wasn't very good, to say the least. So they would take off solvents that were actually ligands. They would remove counter ions. So your framework can actually have a net charge, right? And then you have counter ions to neutralize it. So they removed the counter ions and labeled these all as neutral frameworks, but they're not neutral. They actually had a net charge. So that was a big source of the problem. So that's basically what it is. Basically, they took experimental structures, but the experimental structures have, artifacts from the experiment, and they didn't do it well, I guess, is what you could say.
Okay, so I suggest you can continue the discussion over lunch, during the lunch break, with the next speaker.
Yeah.
One more time. Yeah, we can move to the next speaker after.